Hi, and welcome back. Today is going to be a lesson in EM interference and how it affects the ESP32S3. So let me show you one example. So here I've hooked up my new Chinese DC motor in series with a battery to the relay port on the board, and I have my test harness, and these switches represent the payout switches for winning 2 coins, 3 coins, 4 coins, 7 coins. And this is the coin exit switch, and this is the hopper switch, which is located on this side. So what should happen here is when I boot the board, it should display 0. And when I press one of these payout switches, you should see the number of coins that the player has won on this display, and the motor starts. And as the motor turns, it will trigger the hopper switch one time for each coin, and this number will decrease by 1 until it reaches 0, and then the motor shuts down. That's what's supposed to happen. So let's power it up and see. Okay, it's booted and it's ready. So let's simulate that the player wins 2 coins. That's not supposed to happen, is it? So I initially thought that this was a problem in my firmware, but it isn't. What's happening is that the EM noise from the motor triggers the GPIO pins. So my interrupt routine fires like crazy. However, there is a workaround or a fix for this, and it's a capacitor. So I'm going to add this, solder it to the terminals on my motor, and we'll try again, see what happens. I am now soldered on the capacitor to the terminals of my motor, and otherwise the setup is exactly like before. Same firmware, same configuration. I only added this. So let's boot it up and see what happens. Okay, board is booted. Now let me press the payout switch 2, 3, 4, and 7. Yay! It works. No, it doesn't. So once I connected the motor to the same power supply, I got random interrupts from the GPIO pins once again. And the GPIO wiring didn't even have to be connected for me to get those interrupts. So I guess we'll have to run separate power supplies after all. That was one thing. Another thing is that it doesn't fit into the cabinets. So I will have to make an entirely new hopper assembly. So back to Fusion 360, make a model, do some printing, and try again. As it turns out, I think maybe this little mishap was a blessing in disguise, because it gave me a real good opportunity to learn some new stuff in Fusion. For example, contact sets and tangent relationships. Let me show you. This is my initial design for a new hopper. I have this plate here, and I have this slider that's sitting on top of the plate. Between these two, I have a planar joint, planar motion, so it can slide back and forth across this plane. I also have this cam, or this rotor, that can push against this slider. So when I rotate this, it will kind of follow. So the coins will be inserted through this top hole, and once we rotate the cam, once the slider reaches this point, the coin should drop out. I have this top plate where I'm going to mount a small micro switch that will be triggered by this edge here, and a coin tube for collecting the coins. So this will be a stack of coins inside this tube, and when this rotates, it will release one coin for each rotation. So this gave me a good excuse to familiarize myself with the concept of contact sets in Fusion. If you have multiple bodies or components in a contact set, that means that they can't interfere with each other. So they will push against each other if you try to move them. I also used the tangent relationship between this cam and this slider to be able to simulate to make them follow each other. So when this rotates, there will always be a tangent relationship between this face and this face. The physical model will have springs mounted on the end of the slider and to this bracket here, so that will push the slider back. So I'm 3D printing this now, so we'll see how it turns out. These are the major components. This is the bottom plate, and the slider is going on top of this. It's going to slide like this. So if this has a coin and it slides there, the coin drops out. This is going to be driven by a cam. Just attach that like so. And we'll attach the top plate using 4 countersunk M3 screws. Okay, so this can slide freely, and when it's in the extreme position it will trigger this micro switch here. To be able to return to the original position after each turn, I'm going to add some springs. This will go between these 2 points. Like so, and one on the other side. So now it will return to the original position after the coin has been paid out. Yeah, so we just have to add this coin tube and then we can hook it up and test it. I have now hooked it up to my benchtop power supply and it's set to 12 volts, so we can see if it runs at all. Yeah, so I see I may have to move this switch a bit closer Since it doesn't trigger, we can try filling it up with coins and see if it will dispense the coins. Okay, here we go. Yeah. So I think maybe 60 RPM is a bit slow, so we can try and jack up the voltage. So I can try and run it at 24 to see if maybe 120 RPM is better. Yeah. Let's run out. So that looks like it's pretty stable. Now, there is a slight chance that some of you might think that I've overdone this a bit, but if you set out to do something, you should do it properly. So now this thing has a file system, it has a command shell, it's connected to the internet. What else? Yeah, it's running a preemptive multitasking operating system. So let me show you what it can do. I'm not going to go into too many boring details at this point, but I can show you the main structure of the program. The firmware itself is based on the FreeRTOS operating system, and this is preemptive multitasking real-time OS for embedded devices. I start out by initializing the non-volatile storage, and this is where I store parameters for Wi-Fi settings, debounce, delay times, etc. It then tries to connect to my local network if I have stored the necessary credentials. And then it initializes the GPIO pins and displays 0 on the display. It then proceeds to initialize the SPIFs file system. This is where I store my certificate bundle and my private key. And this is used for communication later on. I then create an event queue for bookkeeping data. So when you insert a coin into the game, an event will be generated. And when a game pays out a number of coins, corresponding events will be generated and sent to this queue. I then start the 3 main tasks in this program. The first is a console task, and this gives us an interactive shell. I can show you the details of that later on. And this is kind of nice because it allows you to change runtime parameters such as debounce setting while the board is actually running in the game. I also used it for debugging, so I added a few extra commands. The game task, it's where the main game logic runs, and this is probably like 5% of the entire code base, so it's pretty trivial. And I also create a send task. If the device is connected to Wi-Fi, it will read from this event queue and send the data to an IoT backend using DTLS. I'll show you how I set that up as well afterwards. So this is the main program. Okay, so what you see here is a console output. The board is connected via USB, and that can be used for accessing the console as well as flashing the board. So I based this on an example code base from Espressif and extended it a bit. So it has a help function to show you which commands you have available. We can look at the running tasks. We can see if it's connected. If I enter IP, yeah, I got an IP address. We can look at the delay times. So these are the delay times that the game will try to read from non-volatile storage. So I can change this on the fly if I want to. If I want to change the delay for the hopper switch, for example, I will type something like set delay hopper 300 milliseconds. Now that's stored, so it will survive the next boot. We can try and read it back. Yes. I can also see if I can reach our IoT backend. Let's see if we can send a live message. Since my screen capture utility isn't working very well, I need to film my monitor. It's embarrassing, I know. Okay, I'll power on the device and we will enter the monitor mode. See if we have an IP. Yeah. So now I'll try and send a test message to our IoT backend. This tab here shows the admin console of our backend. So I have several collections of devices. Under Time Expander I have one device, and this has an inbox, and here you can see the latest messages received. So if I send a new message using the tx test command, it says message sent, and if I refresh this, yeah, I got a big message. So I can look at that here. So here we see the payload. It's base 64 encoded. I can try and decode it, and it says Spar 7 says hello. Beautiful. It's finished. I'm going to test it, but first we can take a peek inside to look at the 3D printed hopper assembly and mounting brackets. I had to print a few additional details, like these guides to make sure that the coins don't go all over the place, and also some brackets to keep the hopper assembly in place. So the coins come through here, and when this fires, the coins are released into the payout. Look, money, 50 kroner, barely enough for a bus ticket. Let's apply power and start gambling. Let's just hope that this doesn't catch fire or explode. Really good at this. Didn't accept that. No. This is hard. Close. No. Jesus. I spent almost half my money on this. Ah, so close. Even more. I'm on fire almost. Yes! Jackpot. I'm going to get a faster motor to increase the speed of the payout. I also want to see if we received any messages during the playtest. The board should send out a message for each coin going into the game and each coin being paid out. So if I look at my Time Expander collection inbox, and here we can see the messages a few minutes ago. These are persisted in the backend, and I can make a small application for my phone or my computer to retrieve this and generate bookkeeping info. I think maybe that's an exercise for a later date. Of course, everything is checked into GitHub. For the time being, this is a private repo, but by the time this video is released, I'll make it public. Just have to add a few notes and comments to document it. You'll find firmware, step files, STL files, Fusion 360 model. You'll find Eagle schematics, PCB layout, and CAM files, if you want to make one of these for yourself. So I'll document how to build flash monitor and shell commands I've implemented, and try to describe the changes you need to do to your game to make this work. And I also added some notes about the IoT backend. I'll add some links to the GitHub repo and to the IoT backend in the description, in case you want to play with that. It's really handy if you're into Wi-Fi, wireless IoT stuff, cellular IoT stuff, etc. I've already gotten some requests for purchasing copies of this board, but I'm not going to sell it. I'm going to give it away. That is, I'm going to release the source files publicly on GitHub. So if you want one, you have to make it yourself. Sorry about that. Until next time, bye.